do this?
In a sense. So you guys, I want to top my 64-foot apartment complex. Hurl my calculator upward at an initial velocity of 48 feet per second. Now I know today, or excuse me, tonight, I cannot come up with this mathematical model out of thin air. If you guys give me till the end of the semester, I will be able to do this. But for now, just trust me that I think after t seconds, the height of my calculator could be -1/2 the acceleration due to this particular the gravitational pull for this particular planet, using British units. T squared plus the initial velocity times t plus the initial height. And I'm sorry if that sounds like mathematical magic. It is. But again, I'll justify it. So, I got a question. Number one. What is the rate? Of change for h with respect to time t.
Is it not the derivative?
Yeah, I think it is just a derivative. And to use some appropriate notation, how about if I use that Leibniz notation? Let me think of the derivative for h as dh dt. Tell me what again?
-32 t plus 48.
What about this question? When it 0, 1. See, I agree with that. Since the initiative is going the upward direction, I think the max height is going to be reached when it actually changes direction. At that one moment for which the rate at which a height is changing will be 0 to solve the equation. Where dh dt is equal to 0 simply means to solve the equation. I can't read that. Is that a -32t plus 48?
Correct. Yep.
Is equal to 0, or shall I say d is equal to, is that a positive 3/2? Oh shoot. Could we have used math d to answer this question?
Couldn't you just find the vertex?
In this example, I gotta confess, since the function h has to be quadratic in t, therefore graphically speaking, it's a parabola in terms of t, I do think maybe I could just find a vertex by looking at -b/2a, or maybe complete the square. I'll get the same answer. I do think, however, in saying the derivative equal to 0, I think I can actually answer this question even if this function is not quadratic, as long as I can solve the corresponding equation. So I do think there's more power the way I'm approaching it this time around as opposed to how I approached it back on Math D. Anybody?
Plug in 1/2 seconds for t.
Plug 3/2 in. It's t for. I can't speak. Sorry. Plug 3/2 in for t, and I see that dh dt is equal to what?
-32t plus 48.
Say it again.
-32t plus 48.
I think it's this. It doesn't answer the question. Because that gives me velocity. I think to come up with the corresponding height, I should go back to the original equation. Did you guys see my point? Do you guys mind if I don't finish the arithmetic? That's how it comes to come up with maximum height. Are we there? So h of 2 minus h of 0.
Except by that question, do you mean
Yes.
like total vertical
Yes.
distance? Like going up?
Why, are you going to change your mind now?
Well, I mean, if you mean like vertical distance, like how far has it gotten from, then you do h of 3 over 2 minus, or h of 2 minus h of 3 over 2.
Well, actually, I think Nabil's right. I think I'm wrong. I don't think this represents the total distance traveled in the first 2 seconds, but Nabil, do this. Initially, the ball was going up. Then after 3.5 seconds, it was going down. So I think for the upward trip, I think the distance traveled actually is the difference between my function h of value 3/2 and my function h of value 0. And I need to add to that the distance traveled over the second part of the trip from 3.5 seconds to 2 seconds, but I think it's going to be the high h value minus the low h value. And I think that's going to be h of 3/2 minus h of 2. Did you guys see that?
I have a question.
getting the 2 from?
Well, over the first 2 seconds.
Oh, I'm sorry. It's just,
Benjamin?
didn't do that.
Yes, can I draw a picture? Let's see, height over t. I think here's what's going on. And I think this point right here is 0, 64. I think this point right here is 3/2, I don't know what to call it, question mark, I'm too lazy to compute it. And then I think after 2 seconds, I get 2, pounds. Don't you agree the total height traveled, I'm sorry, I misspoke. Don't you agree the total vertical distance traveled is the distance vertically from here to here? But that's h of 3/2, there it is, minus h of 0, there it is, I know it's 64. Plus the distance traveled from here to here, the vertical deviation here, but I think that's h of value 3/2 minus h of value 2. So I think I'm just taking into consideration this vertical distance plus this vertical distance. That's all I was doing. Can I beat that clock and not do the number crunching?
Good.
In other words, what's a change of position for the first 2 seconds?
Now you can do what you did for the first.
H2 minus.
Now, I agree with that. I do think no tricks. It's just simply the difference between the position at the end of 2 seconds and the position at the beginning of 2 seconds. I agree. By the way, when it comes to a position function, I know I'm using height, but it's like a position function, a particle moving along a straight line. I think the rate of change of a position function is something that a physicist or an engineer might refer to as,
Acceleration.
well, first derivative.
Oh,
Velocity.
velocity.
Yeah, I think it's the derivative of the position function is simply going to be interpreted as velocity. Or speed, right? Same thing, isn't it? Same thing, isn't it? Yeah, I don't think it's the same. I don't think it's the same thing. After all, when it comes to speed, that's sort of like saying, when I got in my car tonight, came to campus, I drove at an average speed of 25 miles per hour. But when I go home tonight, my average speed is probably going to be... Because I want to get home faster? I was hoping you'd say positive 25 miles per hour. But if my average velocity coming to campus tonight was 25 miles per hour, my average velocity going home tonight probably would be negative 25 miles per hour. So velocity is a vector. It's got 2 components, magnitude and direction. Whereas speed is nothing more than the scalar or the magnitude of velocity. And if I were to look at the second derivative for a position function, which is the first derivative of the velocity function, I'd probably get acceleration. And if you differentiate acceleration, you get jerk. So that could be a physicist's interpretation of the third derivative function. If the original function is a position function.
What comes after that?
Was it death? To the best of my knowledge in applications, I've never come across an application for the fourth derivative function.
Okay.
days from now.
Do you know what's gonna be covered on the 10th?
Whatever we finish on Wednesday night.
Oh, okay. Because he wants to get us.
I take it to section 3.5.
Absolutely.
I don't know.
Yep.
Sorry. So, you guys ready? You read the question?
Well,
We
done this
already did this.
We've already done it, but if you guys don't mind, I'm going to scroll down because I've added to this. And if you now know what that function big T is, what can you say about the average cost function? I mean, a big T is a total, did I say cost? You guys, I think I mistyped. What did T represent? Total life earnings. I'm so sorry. When I say cost, I mean earnings. Boy, that was bad. So let's determine the average revenue function. How would I do that? Nobody?
You take
The initial-
derivative of it?
But how would I come up with the average revenue in terms of X?
Oh, just find total revenue divided by time.
Divided by
Years.
Oh, how about this? I think my T of X is simply going to be my T of X divided by X. Because I'm taking the total earnings divided by whatever that quantity X represents. In this case, that represents time. Do you guys agree? And yes or no? Could you differentiate this?
Yes,
Yeah.
Yeah, you certainly can. And so I think to differentiate, I'm simply going to get what's downstairs times the derivative of what's upstairs. Minus what's upstairs times, whoops, hold it. Minus what's upstairs times the derivative of what's downstairs. All over what's downstairs twice. And I don't want to finish a problem because technically speaking, we've already computed T prime of X above. I'm cheating and stealing my work from last time. So, what the heck would this represent? If I evaluated big T bar at 10, what would it represent? So it would represent,
The average revenue over 10 years.
good, I think it's the average revenue per year, but only over the first 10 years. Whereas T bar of 20 would probably be a different value because that'd be the average revenue per year, but over a 20-year period. So the quantity would differ. You guys agree? I'm tired. I want to beat that clock. I've got too many things to say tonight. If I came up with a number for the derivative of big T, bar of 10, what would that represent in words? Who cares what the number is? I just want to talk about concept. What would that represent?
How much you made in the 10th year?
I think that would be big T of 10. But what about big T bar prime of 10?
How fast change in average
How
revenue?
fast the changes in the
Average.
average yearly income after the 10th year. So I think that would be the increase in the actual average revenue per year for the 11th year. In English, that's what that value would represent. And if you guys don't mind, I'm going to be lazy and not compute the number. I just want to talk about the concept. Yes. I think what this number would represent is, on average, what the income is per year at the 11th year. In words. So you guys, that's why I brought this up. I just want to augment those examples.
And it's the 11th year because,
Here's why. You know, if I were to graph that function big T bar, no prime. And whatever it looks like, x-axis, y-axis. Then I think at t being equal to, or x being equal to 10, I think if you guys were to take a peek at the slope of this tangent line right here, the slope would actually be represented by big T bar prime divided 10. It's just that if this is the slope of the tangent line and it equals some number, how about 0.5? I think what that really represents is how fast or how far the y values would decrease, in this case over negative, if I increase my x values by 1 unit. Because I'm looking at the ratio of rise to run. And I think that is the rise for a run of 1 unit. Because this number can be represented as nothing more than self divided by 1. So think of it as rise of a run. I think that's really how far the y values are going to decrease with an increase of 1 unit in the x-axis for the tangent line, not the curve. So technically speaking, this lowering of 0.5 units for a big T of x is really an approximation for the actual decrease in average yearly income over the first 10 years. All right, so you think we have enough examples of this stuff? These rates of change functions?
Yeah.
Okay, if you do.
They're going to compose a lot of our tests.
What's that?
Are they going to compose a lot of our tests?
No, not a lot. No, I wouldn't say not at all.
Wait, you wouldn't say not at all or not a lot?
Not a lot.
Oh, okay.
I didn't say not at all. Well, you guys, you and I have some sophisticated differentiation tools in our back pockets. For example, the power rule, the product rule, or the quotient rule. The last two are fundamentally important for you and I because the last two allow us to differentiate the product or the ratio of two functions. What I haven't discussed yet is how to differentiate the composition of two functions. So if you guys don't mind, I don't want to come to class, I don't want to just spout things off and say, you guys deal with it. I want to be able to say something in class and be able to back up what I'm saying. So instead of just giving you how to differentiate such a composition, if you don't mind, I'm going to drive it. Since I have not discussed differentiating the composition of two functions, I suppose the only thing I really could do is go back to my definition. And I think, if I were to differentiate y prime, can I do it this way? Can I differentiate at a particular value of x? I think this is nothing more than the limit, as x approaches a, of my f evaluated g evaluated a. Excuse me, I misspoke, didn't I? I meant at x. Minus f evaluated g evaluated a, all over the difference between g of x and g of a. Oh, by the way, you guys, I've got an error on the board. I don't know if you see it. I really meant to say I'm differentiating this beast. That's where I got that limit. If you guys allow me to do some algebraic gymnastics within this limit, I think the same as this. The limit as x approaches a of my f evaluated at g evaluated at x minus f evaluated at g evaluated at a divided by how about question mark? Times the same darn question mark over g of x minus g of a. You guys are being a little silly. I'm going to put in here an insertion of a multiplication by 1 in a funky form. Here's my form. You know, I feel like I'm just rushing so much. I'm serious, you guys. I'm taking just way too many blunders. I think I've made a very serious error when I put on the board. Can I show you where it is? And I'm sorry to mess you up. But this denominator is not g of x minus g of a. Isn't it just simply this? Just going by my definition of derivative? Seriously, I really did commit that blunder. Can I fix it over here? And if you don't mind, just because it's completely completely legal. I think I can divide the first thing by question mark as long as I got another question mark in the numerator of the second fraction. So let me show you what that question mark is going to be. In red, it's exactly what I erased over there. However, you and I are well versed with limit theory, and we do understand that the limit product is a product of two limits. So I guess I've got the limit as x approaches a of my f of g of x minus f of g of a over g of x minus g of a times the limit as x does its thing of this particular ratio. But if g is a continuous function, I maintain that as x approaches a, then g of x is also going to approach g of a. And you guys allow me to make a substitution. Just to make the notation look a little bit nicer. Whenever you see this g of x, let's call it a name. Let's give it the name of just y. And for simplicity's sake, if ever you see a g of a, if you so choose, you can replace it with a constant b. It's just a constant. If I do this, then I think I can rewrite the first limit as my f of, I forget my letter, is it y? Minus my f of b, all over my y minus b. And by the way, if g of x is now called y and g of a is called b, I guess that means I'm taking this limit. That's being multiplied by this particular limit. It's just this time around, I'm not going to change any names. Okay, you guys, here's my punchline. This is a big deal. Would you not agree that when you look at the first limit, by definition of derivatives, isn't this nothing more than the derivative for f with respect to y, but evaluated at? And it's being multiplied by the derivative g prime evaluated at x, but at a specific value, that's namely but I think this is nothing more than f prime of what was the old name for g for b? G of a times by g prime of a. This is so fundamentally important, I give it a name. I refer to this differentiation process as a chain rule. Is how I differentiate the composition of two functions. So you first have the product rule, then the quotient rule. Now we've got a differentiation process for differentiating composition of functions. Let me officially state it since I've just proven it. I think to differentiate with respect to x, the composition of two functions with respect to x, I'm going to differentiate the outermost function and evaluate it on the innermost function, period. But I'll multiply that by the derivative of the innermost function.
Is that also true if you've got like f of g of h of x?
Yes, I can apply the chain rule twice, and I will tonight.
Okay.
I'll do it repeatedly. Some people write this differently. Some people say to differentiate y with respect to x, chain rule using Leibniz notation looks a little bit different. We can think of this as a derivative of y with respect to some intermediate variable times the derivative of that intermediate variable with respect to my independent variable. It's just the same darn thing. So let's see if we can look at some examples. Would you guys agree that is a composition of two functions? So if I actually plug a number in for x like a 2, what are you going to do with the 2 algebraically to evaluate this mess? No derivatives, no calculus. What would you do to the 2 first? Square it, then you would take the sign of it. And if that's your order of operations, then differentiating with a chain rule always goes in the opposite direction. I'm going to differentiate the outermost function first. But through the outermost function is a derivative of the sine function, and how do you differentiate the sign of anything? You get the cosine of that thing. But the chain rule says I got to multiply by the derivative with respect to x of the innermost function, which, by the way, merely gives me a 2x cosine of x squared. would you soak that in for a minute? That's applying the chain rule, differentiating the composition of two functions.
Could just do the product rule on that one, right?
Unfortunately, I can't. It's
Really?
because the innermost function was being squared.
Okay.
Not the whole thing.
But I mean, if you
The
just
whole
did
thing's not being squared.
sine of x times sine of x, you could
Unfortunately,
do that with
this
the
thing right
product rule.
here
Yeah.
is not the same as this.
Ah,
I think this thing right here is really the sign of a product, but I still got composition of functions. And so before tonight, I couldn't handle this particular derivative. What would you say about this one? Oh shoot, you guys, I don't want to waste time in class. We've already done that, so can I go to another one? How about number 3?
that one you could do the product rule, right?
Ah, so I can't go that fast. I think there's a completely different deal.
Yeah.
I may still be composing the sine function and the squaring function, but in the opposite order, because if you plug a number for x, like 2, won't you take the sine of it first, and then square the result? So I think I might be composing the same two functions I did before, but composing in the opposite direction. Let's differentiate using the chain rule. Chain rule says you differentiate the outermost function, which is the squaring function, by wrapping your fingers around the 2, pulling down to the level of everything else by multiplication, and reducing your exponent by 1. Oh, but the chain rule says I got to multiply by the derivative with respect to x of the innermost function, which is the sine of x. But what's this derivative? I agree. Anybody want to take a mathematical broom and clean it up?
Ooh, isn't that a...
Sine of 2 theta, or
Yeah.
2x.
Very nice. I agree.
Every word right, so like my old teacher told me, like every word right, so you understand, is just type in sine x and then parentheses and put a square outside of it.
Absolutely. Absolutely. So how about another question? How about differentiating this time with respect to x, the sine squared of x? So you ready?
Ready.
What's that?
Ready.
Are you really ready?
No.
Uh,
It's tired.
it's a typo. I've already answered the question.
Do why? Oh.
But if you guys don't mind, let me just answer the same question in a different way. I can think of what's inside the parentheses as a product of these two things. If I really wanted to. No chain rule. Using the product rule, that gives me the first times the root of the second, plus the second times the root of the first. But that gives me 2 sine of x cosine of x. Oh, thank goodness, I get the same answer. Just a different way of getting there. This time, I really could have used a product as opposed to chain rule. Come on, you guys, you're too quiet. Give me some feedback.
Wait, how?
Because it's sine of x times sine of x.
But where's the product rule?
Well, I differentiate this product. The product rule says I got the first times the
No, never mind. I'm thinking power rule. I'm sorry.
Did you just say that it would only work for this example, that we could do both these ways, or is it that we could use it for this?
I think in my second example, I had a choice between the chain rule and the product rule. But I think in my first example, I did not have a choice.
Okay.
Because the multiplication actually was embedded in the sine function. Therefore, I still would have to use the chain rule. Even if I wanted to rewrite x squared as x times x. No way around the chain rule with the first example. There was a way around it for the second example. Yes?
Can you go over the inner and outer on 1 and 2 there?
Well, I think what the chain rule says up there is that I really get... Can I restate everything, Steve? Let's do this. If y is equal to sine of x squared, and I want to think of this as f divided g of x, wouldn't it truly be the case that the outermost function is just a sine function, and the innermost function, the g of x, is just simply the squaring function? You guys double check me if I made a mistake. Going backwards, if you're to compose f with g, wouldn't you just plug this in for x? So I've decomposed that function here into the composition of f and g, where f is sine of x and g is x squared. And so I think the chain rule over there says that I'm going to compute the derivative of my function f divided g of x and multiply it by the derivative of g of x. But check this out. Watch. The derivative of f is just cosine, or shall we say the derivative of sine of x is a cosine of x. And so I think f prime is going to be the cosine of whatever the input is. That's just g of x. Times the derivative of g prime of x, but check out g of x. What's its derivative? Oh, I don't like this, you guys. I don't want the g of x in there. I'll substitute it out. Another name for g of x is just simply x squared. Or shall I write it more precisely as 2x cosine x squared? I mean, if you really want to show me how to show more steps. What do you think?
So if you have more than one function embedded into the equation, you just do that twice or 3 times or 4 times or 5 times.
Oh, you mean like my fourth example?
Oh yeah, like that one.
Yeah. Well, shoot, here I think I've got a composition of 3 functions. If you plug the number in for x, I think the first thing you do is evaluate that quadratic expression x squared minus 1 at that value of x. Then you would
Subtract 1.
exponentiate if you did the whole thing. You would now exponentiate. Then you would take the square root. And so now to differentiate from outside in, I got to differentiate the outermost function first, which is the square root function. But to differentiate the square root of anything, what do you get? 1 over 2 roots
X.
of that thing. It's just the chain rule says you got to multiply that by the derivative with respect to x of whatever the heck you're initially taking the square root of, which in this case is this nasty business. I've applied the chain rule once. That being the case, let me dive in. That leaves you with this mess. Now to differentiate e to any power, what do I get? E to the power. Oh shoot, but the power is another function in x. So the chain rule second time around says I got to multiply by the derivative with respect to x of the innermost function, what I was initially raising e to the power of. That would be this quadratic expression. But jeepers, that's just this. Are you there? Yes.
So if we were to write out which f of x, g of x, and h of x were,
In this particular example, I think if you were to think of y being equal to the square root of e to the x squared minus 1 as a composition of f with g with h,
so f of x would be like square root of x,
perfectly put. And then g of x would be
e to the x,
perfect. Finally, h would be,
x squared minus 1.
I agree.
And I just wanted to have a visual.
And you should. I talk a little fast because I'm running out of time. But that would be how I decompose this function to accomplish 3 functions. By the way, can I leave it for you guys to clean that mess up? Anybody? Chain rule or product rule, which one? Both. Product rule how many times? Once. Chain rule how many times? Twice. Let's give it a shot. I think the outermost operation is multiplication. I think that's what I need to deal with first in the differentiation process. I'll use a product rule. I think to differentiate the product of these 2 functions, I get the first as is, times the root of the second. Am I missing anything?
Times 2.
Chain rule says multiply by the derivative of what's initially being raised to the 4th power, which is just root 2. Plus the second as is, times the root of the first, but jeepers, differentiating the first, I'll use the power, I'll bring the 3 down, and reduce my exponent by 1. Are you happy?
That's the way.
to differentiate that first factor, I've got a composition of two functions. I have to multiply this garbage by the root of the innermost function, which is... Oh, you know what, you guys? In this example, I insist. Simplify. Anybody? Anybody? Really?
Garbage. Pull out like two
I will pull out like
terms.
factors, things, like factors. And I think both these two terms have a common factor too. I'll pull out.
They've
I
also
think they have
got
a
an x
factor 2x
squared
minus
plus
1, but
1.
how many should I pull out?
All of them.
Yeah, all of them.
3 is the least number of times season out of the two expressions. How many x squared plus 1s?
2.
The small power I which see that being raised to in either
Yeah.
one of those expansions is 2. Let's talk about what remains standing. Well, did I pull out the 2x minus 1s, all of them? Yeah, I did. Did I pull out all the x squared plus 1s?
No.
No, there's 1 remaining standing. Did I pull out all the coefficients?
No.
No, there's still a
2 and a 3.
4 left over. If I pull out the 2, there's a 4 left over. On the right-hand side of the addition operation, humor me with this. Did I pull out all the x squared plus 1s?
Yes.
I did. Did I pull out all the 2x minus 1s?
No.
How many are left over?
1.
Oh, there's a remaining factor of x. Did I pull out all the coefficients?
No. There's
a
3.
remaining left over. I agree. Oh, it's cleanup time. Actually, what is this mess when you expand it out? Is that a 6x squared?
Yep.
Plus 4x squared is a 10x squared. There is an x term which has got a coefficient of -3. I've got a cost term of +4. I've got a remaining factor of 2x minus 1 thrice. A remaining factor of x squared plus 1 twice. Oh shoot, I forgot my coefficient up front. I'll put it in. This time, I know I'm beating the clock, but I wanted to take the time to simplify. Do you guys agree? Yes.
I didn't understand why you got the constant 2 and 2x.
You mean this thing right here? How about this? Would you agree with the following? That to differentiate question mark cubed, don't I just simply bring the 3 down and reduce it to 1? It's just that the question mark happened to be a whole other function, call it g of x, call it 2x minus 1. I think the chain rule says I got to multiply that by the derivative with respect to x of the innermost function. This really is my g prime of x. It's just the derivative of 2x minus 1 is just simply 2. So I called it such. Somebody else had a question.
You actually had a 2x up there.
2x. I think you wrote.
Oh shoot, you guys, you're right. Oh, I'm so
Yeah.
sorry. When I called it question mark and put it back in, I put the wrong thing in. I'm so sorry. Was that question mark? Was that question mark? So this should be times the derivative with respect to x of my question mark.
2x.
I just wrote the wrong expression in there. But the derivative of that beast is.
2x.
Is that helping? Shoot, you guys, my examples, they're too hard. You guys just don't want to have fun.
Wait, is that root tangent or tangent?
Tangent of root. Got the composition of how many functions?
3.
How many? 4. The innermost one is going to be the x squared plus 3. The next outermost one is going to be the cosine function, then the square root function, then the tangent function. So to differentiate, I'll have to use the chain rule. Price. Let's do it. What's the true of the outermost function? The secant squared of whatever the mess is.
Why wouldn't you say that x